Okay, so welcome everyone to the SPDE seminar. So our speaker today is Sandra Cerrai from the University of Maryland. Sandra did her PhD in 1998 at the Scuola Normale Superiore in Pisa. In 2001, she became associate professor at the University of Florence before she moved to the University of Maryland in 2008, where she's currently right now. Her research interests include multi-scale stochastic systems and in particular, stochastic partial differential equations. So we're very happy to have you here and look forward to your talk on the Smoluchowski-Kramers approximation of infinite dimensional systems with state-dependent friction.
So, Carsten, thank you very much for the introduction. Thank you very much for inviting me to give this talk. And yes, as you say, today I'm going to talk about some results about the Smoluchowski approximation for stochastic wave equation, which have some damping term, which is a state dependent. So this is the class of equations that I am considering. So as you see, this is a second order equation in time, which is, a wave equation with this damping term, this nonlinearity f, and then the equation is perturbed by this stochastic term, which is of multiplicative type. This equation is an equation that I consider in a domain, in a bounded domain of RD. And so I'm giving a boundary condition. In this case, I'm giving a Dirichlet boundary condition, but you can take a more general boundary condition. And then I give initial condition for the position and for the velocity. And the Smoluchowski-Kramers approximation is about, you see, studying the limiting behavior of the position of u mu as this small parameter that is put in front of the second derivative in time that can be considered as the density mass of particles moving in a continuum. So I am interested in studying the limiting behavior of this u mu as mu goes to 0. So this approximation is used all the time. So when you believe that somehow the mass is negligible with respect to the other parameters that are in the equation, it is somehow natural to replace this second order equation in time with a corresponding equation which is first order in time. And this is what usually is done, and this is what the Smoluchowski-Kramers approximation. And what I was trying to do in this past year is to give a mathematical justification of this approximation. And also, you see, what was important for me was to see how this approximation was stable or unstable with respect to other asymptotic features of the system. So, for example, the long time behavior, the small mass, the small size noise, and you see other features of this type. Just to fix a little bit the notation, I will give you more detailed assumptions later on, but just to fix an idea of what we are considering with this equation that is written here, you see there is this mapping gamma that is in front of the derivative, which is the damping coefficient, and what we assume is that this gamma is a strictly positive and bounded function. And then concerning the nonlinearity here, for what I'm talking about, you see, I keep this simple, so I consider f Lipschitz continuous and satisfying some growth condition. But in fact, for some of the things that I'm going to discuss, one can take a more general type of nonlinearities, which somehow are more interesting in applications. For example, you can take polynomial nonlinearities and other class of nonlinearities. And concerning the stochastic perturbation, what we assume is that this object here is a cylindrical Wiener process, which is a white in time, but is a colored in space. And you see here, I am putting myself in a situation in which I don't have troubles with the regularity of the noise. So the noise has all the smoothness in space that is required. not only for the analysis of this equation, but also for the analysis of the limiting equation. And then you see, as I was saying, this was exactly what I was saying. What we assume is that this sigma is a bounded and Lipschitz continuous operator, which acts on the space of Hilbert-Schmidt operators that are defined on the reproducing kernel of the noise with values in the space of square integrable functions. And yes, this is what I was saying before. In what I'm talking today, in what I'm describing, in the results that I'm describing today, I'm taking F Lipschitz, but in fact, one can take a more general type of nonlinearities. As I was saying, the Smoluchowski-Kramers approximation is about the analysis of the limit of u mu, the position, when mu goes to 0. And in the case of a constant friction, gamma, so you can take, for example, gamma equal 1, together with Mark Freidling, we have studied this approximation. And what we have proven is that, you see, when mu goes to 0, u mu converges to the solution u of the corresponding parabolic problem. So you see, this is exactly the same equation with the same coefficient, but you see, let me go back here because this is really, I'm sorry. Yes, you see here, so you can neglect this term, so you can take formally mu equals 0, and you get exactly the parabolic equation. Okay, so this was the result that Mark Freidling and I proved for this. And in fact, what we could prove is that if you fixed a time interval 0 capital T, then you have the convergence of u mu in the uniform topology of C0T with values in L2 in probability as mu goes to 0. And this was the first result, the beginning of this series of results. And then, in fact, with Mickey Salins, we could prove that we have a better than convergence in probability. Actually, we have a convergence in LP sense, at least for some class of nonlinearities.
Sandra, so you're working in 1D or?
No. This is D is, oh, sorry. Let me take a D is a subset of RD, and here D is a greater or equal than 1. Of course, you see, I have different conditions on the color of the noise depending on the dimension, but this result is in dimension D greater or equal than 1. Then, if you want to consider some more sophisticated type of nonlinearities, so for example, if you want to consider F polynomial of odd degree with the leading coefficient strictly negative, then in that case, you have restrictions on the dimension. And so you see, you are free to consider any dimension if you are with F Lipschitz. If you don't have F Lipschitz, then you have all the troubles that you have also with deterministic wave equations, and then you have to consider restrictions on the dimension. Okay, but here the restrictions of the dimension are not coming, you see, from the problems that you have with the fact that you are dealing with an SPD. The problems with the dimension are already at the deterministic level because of Sobolev embedding and all these troubles that you have. Okay.
Sorry, I have a question.
Yes.
So the reason you're considering the color noise is purely because in the white case, the equation does not make sense, or?
So if you think of the stochastic wave equation, it depends where you work. You see, the stochastic wave equation, you can consider this as a system, a position and velocity. And if you are considering dimension D equal 1, F Lipschitz continuous, and you are just interested in having solutions in L2 times H minus 1. So the position is L2, but the velocity is a distribution, is only in H minus 1. Then you can consider space-time white noise. As soon in a stochastic wave equation, you want to consider solutions in H1 times L2, then you immediately need to color the noise, even in dimension equal 1. And in fact, you need to take Q star, or if you want, you have to take, yes, the covariance Q to be a trace class operator. So in order to give it, of course, this is if you want to study this equation in the classical setting of function valued solutions and everything. Then you see now there are people that are considering the well-posedness, at least local in time, of this class of solutions with a much, I mean, a worse noise. I've seen that Aurélien is going to give a talk in this seminar, and he has results in this direction. But if you want to work in the classical setting of function value solution, global existence, global well-posedness, and everything, you need to assume a condition on the noise. Is this answering your question?
Yeah, thank you.
This was about the convergence, and then yes, you see in the equation that I wrote, I was considering a single equation, but in fact you can consider systems of equations, and so in that case you replace your constant friction, which is just a number, with a matrix. But as soon as this matrix has all its eigenvalues with a strictly positive real parts, all what you do with a single equation can be done also for a system of equations with minor changes. Okay, so at this level we can work with system, but what is important is exactly this condition here on the eigenvalues of the matrix A. You see, this is what I discuss is when you have this constant friction. But then it's also of interest to study this small mass limit when you don't have a constant friction, but for example, you have particles that are subject to a constant magnetic field. And so you see the damping term now is replaced by this term where this M is a constant magnetic field. And in that case, you see, instead of having a friction, you have a rotation. And so you are in trouble because that matrix that I was mentioning before, whose eigenvalues have to have strictly positive, the eigenvalues need to have a strictly positive real part. This is not anymore the case because here you have a rotation. And in fact, it is possible to prove just by looking at what the solution has to be. You see, you can prove explicitly that the limit does not exist because due to the presence of this noise, you have highly oscillating terms which cannot converge, okay? And so this is not anymore a sort of, I don't know how to say, perturbative result. You just take mu equals 0 and you get the limit. What we could do in this case was to regularize the problem by adding a small friction, and then in the double limit, first you take the limit as the mass goes to 0, and then you take the limit as the size of this friction goes to 0. You are able to get a limit, and at the limit you get an SPD, which is not anymore an SPD of parabolic type, but is an hyperbolic SPD, because of fact, I mean, of this rotation that you have due to the presence of the magnetic field. Then you see, of course, you see, I think it's a quite natural question, the question to ask. I mean, it's quite natural to ask what is going to happen when instead of having this constant friction, one has a friction that depends on the state. So when you have this term here, for some function gamma now, that is a non-negative function. And then what you realize is that this is not just a minor change, which, I don't know, may create problems from a technical point of view, because already having a non-constant friction term creates problem also in the study of the well-posedness of the stochastic wave equation. But it's not just that. What you discover is that things are drastically different in this case. And this is what I studied with Wang-Yu Shi, which is a postdoc here at Maryland. And what we showed is that, you see, in this case, we don't have the convergence to the SPD that one would obtain just by taking mu equals 0. But in fact, because of the interaction between the noise and this coefficient gamma that is not constant, what one has is that at the limit one gets a stochastic, a quasi-linear equation, where you see there is the creation of an extra drift. And this extra drift really comes from the interaction between gamma and the noise. So it's a sort of noise-induced drift. So where is this drift coming from? And I think that there is a very simple explanation of this. If you look at the term gamma u times the derivative in time of u, you can see this as the derivative of a new variable g of u mu. G prime here is equal gamma. And so instead of looking at the limit of u mu, it's probably more natural to look at the limit of g of u mu. So you have this new variable, and it's for this new variable that you want to study the limit. And if you study the limit for g of u mu, what you discover is that you again have a result of perturbative type, in the sense that you have the limit to the equation that you would get by taking mu equals 0. But then the point is that if you want to go back to the original equation, so if you want to understand what is the equation satisfied by the limit of u mu, because of course, if you have a limit for g of u mu, then you have automatically a limit for u mu. But what is the equation satisfied by this limit? And what you have is that in this transformation, you have to go through the Ito formula, and then this Ito formula is providing you this extra term which comes into the limiting equation. I will describe this in details later on, but this is really the whole idea. And of course, here there are further developments. So the first development that one would like to understand is what happens when instead of having one equation, you have a system of equations. So in this case, if you take gamma as not just as a scalar function, but is a matrix valued function, then you cannot say anymore that gamma of u dtu is the derivative of some function of u, okay? You don't have this anymore. And so this transformation is not anymore available. And then you see the analysis of this limit and the identification of the limiting equation becomes, I mean, a more complicated task. And this is what actually, I mean, I'm trying to work now with some progress, but this is not yet completed. And then you see the other direction that one has, and because of some heuristics, some computation that we did, we expect that the very same situation is happening when you have a constant friction, but somehow you confine your solution to live on a manifold. So for example, you can think of the manifold that is, you see, the set of function in H1 which have, you see, L2 norm equal 1. So these solutions are confined to live in the unitary sphere in L2. And so also in that case, in spite of the friction being constant, you still expect to have in the limiting equation the creation of some extra drift. Now, very briefly, one of the interesting aspects in the analysis of this small mass limit for this class of infinite dimensional stochastic systems is somehow that from a second order system, you go to a first order system. And you know how, you see, from many point of view, working with a first order system is easier than with a second order system. So when you think that the mass is negligible, going from the second order equation to the first order equation is you see, is an important simplification. But then, of course, you want to understand how this approximation is stable with other important features of the systems that you want to investigate. And so what we studied was, you see, the comparison between the long time behavior of the second order equation and the long time behavior of the first order equation. And we did this both in terms of convergence of stationary states and also in terms of the study of quasi-potentials and exit times in case of a small of a small noise, so in the framework of large deviations. And in both cases, what we could prove is that this approximation is stable. So for invariant measure, we could prove that if you consider a family of stationary states for the second order equation, sorry. Yes. So what we could prove is that one has the convergence of these stationary states to the invariant measure of the parabolic equation with respect to some Wasserstein distance that has to be built accordingly to the structure of the equation. And also we could prove the convergence of the quasi-potentials and of the asymptotics of the exit problems for the second order equation to the corresponding one for the first order equation. So this approximation is really stable with respect to these features. So it's not just in a fixed time interval, as the statement that I gave you at the beginning was saying, but is something that works on an infinite time frame horizon. And these were papers done together with Nathan Glatols and Mickey Salins. So very briefly, just to give you a more precise idea of what sort of equation I'm considering. So here, D is a bounded smooth domain in dimension D bigger or equal than 1, and H is the reference Hilbert space of L2 functions. And then L is the realization of the Laplace operator with the Dirichlet boundary conditions. So EK are the eigen functions, alpha K are the eigenvalues. And then, of course, I have to give you the functional spaces where I'm studying this equation, and I'm studying this in a very classical settings. So I'm working on these product spaces of H beta times H beta minus 1, where these H beta are the Sobolev spaces that I construct in terms of this operator L. So up to here, everything is absolutely classical. And then concerning the noise, as I was saying, WTQ is a cylindrical Wiener process with some, which is colored in space, and the space covariance is a QQ star. So formally, you can write your cylindrical Wiener process as this formal sum. And here in this sum, we have the operator, we have this operator Q, we have the eigen functions EK, and then we have a sequence of independent Brownian motions, all defined on the same stochastic basis. Yes, in what follows, this HQ is a fundamental object and is the reproducing kernel of the noise, which is just the image of the space of square integrable function through the operator Q.
Sorry, can I ask a question? So, like the main reason to consider the bounded domain, like instead of the four spaces, it's because.
Huh?
I mean, like, what is the main reason to consider the bounded domain instead of?
I studied this in the setting of a bounded domain, and working with the bounded domains is helping me a lot. For example, you see already this decomposition of the, you see, I don't know if you have some familiarity with this, but if you, instead of working with a bounded domain, you work on RD, then you cannot have anymore this representation of the noise. This representation of the noise is based on the fact that you are working in a bounded domain, so you can diagonalize the Laplace operator, and you have this family of eigenfunctions, eigenvalues, and everything. If you are working on RD, then you still can use this cylindrical Wiener process, but you have to introduce a different sort of notation. So you have to think of your cylindrical Wiener process as a Gaussian field, and then you see typically you take homogeneous in space Wiener process, but you see is a bit different. And I'm not saying that you cannot do this analysis, this particular analysis of the Kramers-Smoluchowski approximation in unbounded domains, but many things should be adjusted in what I'm saying. It's not exact. It's not the same.
Okay, thank you.
So concerning the diffusion coefficient sigma, as I was saying, is nice in the sense that maps H into the space of Hilbert-Schmidt operators defined on the reproducing kernel. And I give this structure of sigma, and this particular structure of sigma is somehow needed in the study of the limiting equation that, remember, is a stochastic quasi-linear parabolic equation, which in itself is not a super trivial object. And so this particular structure is required in order to, to study the limiting equation. And then you see I have a nice Lipschitz regularity for this coefficient, which is given in this form. And so in particular, and this is important, what you get is that with this assumption on sigma, what you have is that the mapping that associates to every x in the domain this series, this mapping belongs to L1 of D. So because of the assumption on the coefficient sigma, this sum is convergent and is L1 in the space D, okay? And this is fundamental because this is, you see, part of the noise-induced drift that you will see at the end. So concerning the friction term, here I'm putting myself on a very nice situation. So what I'm assuming is that this mapping is smooth, is C1, and is far from zero and is bounded. Okay, so it's bounded from below and from above, and strictly positive. And this means that you can define this integral, and this integral vanish at zero is equal gamma and is strictly increasing. And this is the gamma that provides me with the transformation that I was mentioning at the beginning. Here, many things are still to be done in this setting, because here I'm assuming that gamma is strictly positive and it's bounded. If you remove one of the two, it's not just you have technical problems, you have different problems, okay? And so, for example, having a gamma that is not bounded at the limit give you, a quasi-linear parabolic SPD, which is degenerate, and so you have to go to the, you have to go through the analysis of this degeneracy. And if it's vanishing, then you see you are in big troubles for many things. And I think that it would be interesting to study these cases, so to see what happens in these cases. And the reaction term, yes, I'm assuming that this is a Lipschitz continuous function. And you see, because of, I think these are technical problems, you need either sublinear growth or linear growth with some control on the Lipschitz constant of this function. I don't know how deep is the reason for this. This is a problem that you have when you want to do your a priori bounds. I don't know, really. if this could be extended. So once we have this, let's see what we can say about the well-posedness of the system, which in itself was not something that was available in the literature. So this was not clear how to give a sense to this equation. But you see, you write your wave equation as a system in this form. And then one way to study this equation is to do a simple change of variables. So you consider eta equal the derivative of u plus this term here. And so with these new variables, you can write your system as this abstract stochastic evolution equation in this form with, you see now sigma mu is given by this expression, and a mu is given by this expression. And as you can see, you have this abstract stochastic evolution system, and here these parameters depend on mu, and they depend on mu on this nasty way. Okay, they have this 1 over mu that is present both in the deterministic part and in the stochastic part. But you see, with these new variables, what you realize is that your original system in the position and the velocity becomes equivalent to this equation, the equation that I wrote before, and that I can write here in this way just by integrating in time. Okay, so solving the system 5 is the same as solving this equation 6. And that is exactly what we are doing. We are working with equation 6. And at the end, what we get is that if we fix any initial conditions, U0 and V0, which are in H1, which is H1 times L2, so the position is in H1 and the velocity is in L2. And if we fix any arbitrary time interval, what we have is that the equation is well posed in the sense that there exists a unique adapted process that lives in the space of continuous trajectories with values in H1, which satisfies the equation. And this is just done by using some theory of nonlinear quasi-dissipative operators. You see, you see the approximations, and then you take the limit, and you have the existence, and then you have to prove uniqueness. Okay. So once you have the well-posedness, you want to study the limit, okay? So all what I've said until now is for mu fixed, and now you want to see what is the behavior of the solution with respect to mu. And of course, you see, what we want to prove is that there exists a limit, and then you want to identify this limit. And in order to prove the convergence, you see, what you have to use, what you have to prove is some tightness for this family of processes, u mu. And of course, when you want to prove tightness, you need to prove uniform bounds, both for the position and for the velocity. And this is where you see somehow some troubles are coming, because these uniform bounds with respect to mu are quite involved and are not, you see, they do not come from the standard and usual energy bounds that you do for this class of equations. You see, the first one somehow is not particularly complicated, and what you get is this bound for the uniform norm in H of u mu, and for the L2 norm of the norm in H1. Okay, so this is the first bound. And this is a uniform bound with respect to mu. But then the second bound that we could prove are bounds that involve the H1 norm of the solution. You see, having uniform bounds for the solution in H, as you can imagine, is not enough. You want to have tightness, so you want to have some compactness. And so you need to go to H1. And for H1, what we can prove, we don't have uniform bounds for H1 in the uniform norm with respect to time, but what we have are these bounds here. So here we have the supremum for the H1 norm, and then here we have the supremum in time for the H norm of the position, and then we have this bound here for the L2 norm of the velocity. But you see, this is only a bound that goes as a constant divided by mu. So here you don't have uniformity. And from this bound, what we get, however, is that this is a 0. So what we get is that if you consider this term here, and this term here will be fundamental, and you will see the role played by this term later on, what we get is that this supremum is finite. So already the previous estimate, this estimate here, already this one has some utility to be able to say that this is something that is bounded. But this was not enough for what we wanted to use. I mean, for the purpose that we had in using these bounds, and so we had to go in a deeper analysis of the system, and then at the end what we got is this, that if you fix a time interval capital T, on that time interval you can find these two constants Ct and mu t such that this inequality is satisfied. So you see, here we didn't get a clean bound. So our idea when we started to do these estimates was to be able to prove that this was less or equal than a constant. This was our hope. We were hoping to prove that we had some uniformity in the norm H1 for the position, and for mu, the square of the norm H of the velocity, a uniform bound in mu. But we couldn't get that, and we had to pay this price. So we had this. And you see, if you compare what you can do in a finite dimension, in finite dimension, you are able to prove a bound like this. You are able to prove a bound like this. But in infinite dimension, this seemed to be, I mean, out of our reach, at least. In any case, this bound was good enough to be able to say that this term here, that with the previous bound, remember, was only the previous bound was only given that this term was uniformly bounded with respect to mu. Now we are able to say that this is something that is going to 0. And here, in fact, we have also the supremum with respect to time inside, okay? But we were able to prove this, and this was what we needed in order to study the limits. So now we go to tightness. And if we want to study tightness, we go to this new variable. We go to rho mu, which is a g over u mu. And we prove the tightness for this family of measures for every sequence of parameters mu k that are going to 0. And in this case, what we did was the following. We have this new variable rho mu, so we have to do the change of variable, and we have to get new coefficients b, f, and s, which of course are defined in this way. And what you realize is that the new variable rho mu satisfies this equation here. Okay, this is and so what you have is what? So this is the variable rho mu, and then you have this term, which you remember was the term that I wanted to send to 0 as mu goes to 0, and then you have this term, term of this type, and of this type, which will be somehow the coefficients and of the limiting equation. So the whole point here is to prove tightness, and we can prove that this term goes to 0, and then you see we can find a limit for rho mu. So we have to prove tightness. And you see, so we consider this family of measure, G of U mu K. And what we could prove, because of the uniform bounds that we prove, is that this family of probabilities is tight in the intersection of x1 and x2. So what is x1? x1 are all continuous paths with values in all possible h minus beta for all beta positive, okay? So I never get to h, I always stay in Sobole spaces of negative regularity, but this is true for every delta positive, okay? And then I have also tightness in x2, which is the intersection of all LP in 0t with values in h. But this is what we can get. We cannot get more. So you see that this intersection and this space here are not included in L infinity 0t with values in h, which was somehow the natural space where you wanted to prove your limit. But this is something that we couldn't reach because of the uniform bounds that we got. And the proof, of course, of tightness is derived from the energy estimates that I described before. And then you see, by using suitable characterizations of relatively compact sets in space of Banach, I mean, on Banach space valued LP functions. Okay, so this is quite classical once you have these energy estimates. Okay, so now we have tightness, so we have convergence of subsequences, but we want to have convergence to a well-defined object, and this will also allow us to get a better notion of convergence, not just convergence in distribution, but convergence in probability. And so we have to identify the limiting equation, and for the limiting equation what we have is that you see rho mu will converge to this equation here, and this equation here you see is a quasi-linear parabolic stochastic PD, where the coefficients are the same that I described before. This class of equations, and you see this B now is a nice coefficient, so this is a quasi-linear stochastic PD of the good type, because this is non-degenerate, B is bounded, so this is in the right direction. I mean, this is a good coefficient, okay, because of our assumption. So you see how fundamental were those bounds, and if you don't have one of these bounds, then you are in trouble. This is the notion of solution for that equation. What we have is a solution in strong sense in the probabilistic sense and weak in the PDE sense. So you integrate by part and you get a solution in this form. And what we approved is that for this equation, we have uniqueness of solution. We didn't care about the existence of a solution, but what we care was the uniqueness of a solution. This type of equation had been studied by several authors, the beginning by Debush, Vauvel, Hofmanova, and then there is a nice and very concise paper by Hofmanova and Zhang, where some of the methods are of the previous papers are simplified in simpler situations. And you see that their work didn't completely cover our work, so we had to generalize some of their arguments to prove through a Nito formula for the L1 norm of solution, we could prove uniqueness and for this equation. And then you see, now we are at the convergence result. So what we have is that we could prove this limit. So what we could prove is that the solution U mu of the second order equation converge in probability for to the solution U, which lives in this space of this equation here. And now you see, what is this? This is a quasi-linear parabolic equation. You see, you have this coefficient in front of the Laplacian, and the coefficient is what you expect, is 1 over gamma. And then you have f over gamma. Then you have a sigma over gamma in front of the noise. And then you have this term here, you see, that involves the noise. So you have the terms coming from sigma, q, and then you have the derivative, you see, is given in terms of the derivative of gamma. So of course, when gamma is not changing, when gamma is constant, you don't have this term, and you don't have this term if you don't have a noise. But the interplay between these two things is creating this extra term. And I will describe you now precisely how. So, some words about the result before giving you the scheme of the proof of the result. So if you think of this equation here, look at this equation. If, oh, my, it's not working. I mean, I think, sorry. Yes. Okay, so let me go back here and look at this term here. Look at this. If sigma is constant, then that term, which is minus gamma prime over gamma cube, sum of sigma u q e k squared, this term here is nothing else than the Stratonovich two-eta correction. And so you can say that at the limit, when the mass goes to 0, in the presence of this variable coefficient, what you get is that the solution of the second order equation given with an Ito integral converge to the quasi-linear parabolic equation, which you obtain just by taking mu equals 0, but where you replace the Ito integral with the Stratonovich integral. So you may think that the Stratonovich, so what you get at the limit is the perturbative equation, but with Stratonovich integral. But in fact, if sigma is not constant, that term that I wrote is not the Stratonovich two-eta correction. And so this means that the small mass limit in the general case, when sigma is not constant, doesn't lead to the parabolic quasi-linear equation which is obtained just by taking mu equals 0 and replacing the Ito integral with the Stratonovich integral. So something different is happening. About the proof, I think I have only a few minutes, but I mean, I just give you the main idea, and I think that I already gave you the idea of what you do. You see, due to the tightness that we could prove, the family of measures given by the distribution of this rho mu, you see, they converge weakly, and then by Skorokov theorem, we have convergence in, I mean, what did I write here? You see, you have tightness, so you have a convergence in distribution. Then you, and then you use the Skorokov theorem to identify this limit, and then what you have is that this converges to some rho, okay, which lives in this space, and that satisfies this equation here, which is obtained by integrating by parts with respect to some smooth function psi, okay? So tightness, you have convergence in distribution, and then you use the Skorokov theorem to take the pure more sure limit, and then you identify the limit as the solution of this, okay? But then what you have is that that equation that I wrote, because of the consideration that I said before, has a pathwise uniqueness. And so by a classical result by Jonjian Krylov, extremely useful, what you have is that from the weak convergence, you get the convergence in probability. So now I have the convergence in probability of rho mu to rho. And then you see, you go back to U just by taking the inverse of G applied to rho. And what you have is that since this G is a very nice function, U has the same regularity as rho. And what you have is that U mu converges in probability to U in the same spaces, X1 intersected with X2 as mu goes to 0. And then you see, at this point, you have the equation satisfied by rho, and you want to understand what is the equation satisfied by U. And for the equation satisfied by U, what you do, you have that, you have that U is a G minus 1 of rho. You have an equation satisfied by rho. And so you use a generalized Ito formula that you see was introduced by Perdue and then has been generalized by several authors and had to be generalized even more in this particular setting, but you see, using this generalized Ito formula, what one can prove is that U satisfies this equation. And this is exactly the equation that I was mentioning before. So at the end, what we get is that the limiting object that you get by taking the limit as U mu as mu goes to 0 is a solution of this. And for this problem, you have uniqueness because you go back to rho. For rho, you have uniqueness, and then you get uniqueness also for U. So you have this limit. Okay, so this was all what I wanted to say, and I stop here.
Thank you, Sandra, very much for your talk. Are there any questions? I hear some sounds.
I have one question, but maybe it's not exactly related with the main result. I was wondering, so in Smoluchowski-Kramers approximation, sometimes when there is no like a random term, people also consider the diffusion, underlying diffusion. And then if there is a random term, then I think the underlying diffusion would have this random drift. So is there any study for this diffusion, underlying diffusion of the Smoluchowski-Kramers approximation?
I don't know. It's possible, but I'm not aware of this.
I have another question. So
Yes.
do you know something about the rate of convergence?
No.
So I think you have an inequality, right? So with this 1 over root mu.
What do you mean?
So I think you've shown once.
What I prove is, you see, I go with this very, you see, I go with tightness, and then I prove tightness, right. And then I have this convergence, weak convergence for a subsequence. And then right. You see, I have uniqueness for the limit. And so from weak convergence, so identify the limit, I have uniqueness for this limit. And so this allows to me to have a convergence in probability. But this is all very abstract. So I'm never taking a difference of the solutions and getting any estimate on this difference.
So would that be possible on some simple domains, like, I don't know, a square domain or a rectangular, or
what I can tell you is this, Carsten. In the case of constant friction, then in that case, yes, you have an estimate, because in that case, by using a very you see detailed analysis of the semigroup of the wave semigroup depending on mu, which which include also the friction, by working on a very detailed analysis of this, we could prove the convergence, but in terms, really what we did was to subtract u mu from u, and we got there, you see, a rate of convergence. This is the result that I mentioned when I said that with the Mickey Salins, we could prove convergence in LP sense. In that paper, really, you can take the difference, and so you have a rate of convergence. But I have no idea when you are considering, you see, a coefficient, friction coefficient that is state dependent. I have no idea how to prove how to control this convergence, really. In the constant case, yes, you can do that.
Yeah, I think also in the constant case, when you have a rate, it would be also interesting to see whether you can determine what the fluctuations are. So whether, and especially what equation the fluctuations would satisfy.
Yeah.
Because it's not clear whether it would be a hyperbolic equation or parabolic equation or something mixed. It's yeah, it would be interesting.
Yeah.
I think. All right. Any further questions? Okay, so if not, let's thank Sandra again.
Thank you.
And so our next seminar will be in 1 week, and we have Aurélien Dia speaking. So thank you very much, everyone, for participating.
Thank you. Bye-bye.
Thank you, Sandra. Bye-bye.
Bye-bye. Bye-bye.
Bye-bye.